Hi, in this session we are going to tackle transient modeling, which is a fairly big topic, so it's a longer than average video. And we will start off looking at the transient term in the general equation and concepts involved with storage in aquifers. Then we'll look at the inputs, both for time periods and steps, and the different kinds of model inputs, discharges, heads, and so on that can be transient. Then we'll look at where the initial heads come from for the start of the very first time step. Got two options there. We'll discuss both. And we'll look at the different kinds of outputs you can generate, from contour plots and vector plots to hydrographs and plots of discharge versus time and so on. And then we'll wrap it up with an example of analyzing a real pumping test with a 9-layer Anaqsim model with a pumping well that was partially penetrating and observation wells that were screened at different levels than the pumping well screen. In a transient model, this is our general flow equation, and this third term on the right side is going to be non-zero because there is a change in head with time in that last term. So when head rises with time, this term is positive and the water goes into storage within our prism over here. And it's easy to conceive that in an unconfined aquifer, if we have head rising with time, the water table is rising and more water is being stored in the newly saturated materials at the top of the prism here. So when head rises, water goes into storage, and it looks in the two-dimensional model like a sink. And when head falls, the opposite's true. Water comes out of storage, which looks like a source. That transient term in the general equation is based on a finite difference time step in Anaqsim, like in most numerical models. And the program assumes that element strengths are constant throughout the time step. And this storage term is computed based on a backward time difference. So our delta H there is the head at the end of a time step minus the head at the beginning of the time step. And when you step forward in time, you can always use the head from the previous time step, from the end of the previous time step. There is a problem at the very beginning, though, because you need an initial head for the start of the first time step, and we'll talk about where that comes from in a minute. The storage flux varies with location, and that means we need to use spatially variable area sinks, like we've talked about in the prior video. The spatial variations that occur in the head derivative with time and with extraction are going to be largest near your stresses, wells that turn on, line boundaries that change head, and things like that. And you'll need denser basis point spacings near those stresses. The storage parameter in a confined domain is the storativity, and in words, it's this. It's the change in the volume of water stored in this prism per unit area, per unit change in head, and it's dimensionless. The storativity is equal to a material property called the specific storage, S sub S, times the saturated thickness. And S sub S does have dimensions of 1 over length. S sub S, in turn, has two terms. The first having to do with the compressibility of water, and beta is the compressibility of water, N is porosity. And the second term is alpha, which is the matrix compressibility. And in unconsolidated materials, this first term having to do with water compression tends to be small relative to the matrix compression, and you can approximate specific storage with this third equation. In Anaqsim, you can input either S for storativity, or there's an option for inputting specific storage, which I like to do because that means your input parameter is only a material property and it's not a function of saturated thickness B. A common way to estimate storativity is by analyzing the early time data in a pumping test, and that's very common. And if you lack that, there's a decent way to get an estimate from equations that were on the previous slide, which are functions of the matrix compressibility of the material. And you can get published estimates of those in textbooks like I'm showing here. This is a table out of my textbook with estimates of compressibility. So you can compute an estimate of specific storage from the equations on the previous slide in a table like this. In an unconfined domain, the storage parameter is called specific yield, S sub y. And basically, when you have a unit decline in the water table, S sub y is the fraction of this volume right here that yields water, that drains. And it's coarser materials that lead to higher specific yields than finer materials in general. Specific yield could be estimated from a pumping test, which requires a longer duration test because the part of the curve that yields estimates of specific yield is the late time part. So here's a pumping test which had 3 steps. This first one, and then the discharge was bumped up again, and then bumped up a third time. And the part of the test that yields specific yield estimates is here, where after it levels off, it starts to climb again, and a later time portion here. So you can do that, but you have to be lucky, basically, to not have some disruption to your pumping test to be able to run it for days and days and days and reach those later time portions. And the other option, which is of course a lot cheaper, is to look to published estimates for similar materials. And this reference here, and I give the reference at the last slide in this talk from the USGS, has a nice tabulation of lots of these kind of estimates. Anaqsim makes use of time periods and time steps in much the same way as is done in ModFlow. Periods are larger blocks of time within which there are time steps, and the time periods define times when the specified model inputs remain constant. And you can make the subsequent steps during a time period grow longer by a factor called step multiplier. So the input table looks something like this, and these are 2 different time periods, and perhaps we had a different recharge rate in one versus the other. Something in the input changed. And the total duration of the period is 15 days in this case. And each of the 2 periods has 4 time steps with a time step multiplier of 2.0. I chose these numbers because it turns out that you get whole numbers for the duration of the time steps. The first step would be 1. The second is twice as long based on that time step multiplier, it's 2. The third is twice as long as the second at 4. And the fourth is twice as long as the third at 8. And these total 15. So that's how the step multiplier works. I usually use a multiplier of 1.5 to 2, which makes for shorter time steps at the beginning, right after a change or a stress, and that's helpful. Lots of different inputs in Anaqsim can be transient, so it's very general transient capabilities. The discharges of either discharge specified wells or line boundaries can be transient. They would change from one period to the next if you want them to. You can also change the heads at either head specified wells or head specified line boundaries. And in addition, those two things can be turned off in specified periods, which turns out to be handy for dewatering applications and various other things. You can modify the normal flux in a normal flux specified line boundary. You can modify the stage in a river boundary. You can change the reference head outside of a head-dependent normal flux line boundary, which is always an external line boundary. For your top and bottom conditions, you can change the flux if it's a specified flux, and you can change the head for a head-dependent flux. Transient inputs are fairly simple to add to your model input. Here's a typical table for a discharge specified well. And in the discharge column, normally for a steady model, you just input one number there. But if you want to make that transient and your transient run has, say, 3 time periods, you just input 3 different values separated by commas. And those will apply to the first, second, and then third and subsequent time periods. So this could be the input for a simulation with 5 time periods. It's just that in the third, fourth, and fifth time periods, minus 560 would be the rate that applies. With head-specified wells and head-specified line boundaries, it's possible to turn them off for selected periods. And in this example right here, we have a head-specified well where the heads specified are 12, 12, and then 6 in the first 3 and subsequent time periods. But in this final column, I've told it to turn this thing off in the second time period. So this number is ignored, and there is no head specified well discharge. It's turned off in that second period. This can be handy in a dewatering scenario where maybe you have a first stage of dewatering wells that you pump, and then as the pit or excavation gets deeper, you turn those off and you turn other ones on. As I pointed out before, for the very first time period, you need some source for your head at the start of that first time period. And you have 2 options in Anaqsim. One is to use constant heads, and that means constant over the area of the domain. And in the domain input tables, there's a column for average head. And if you've chosen to have your initial heads be constant in a transient simulation, that's the head that will be applied in a domain. So here we have 2 domains, both of which would have an initial head of 110 if we had chosen constant. The other option is to get the heads from a file based on the heads in a prior simulation. And you can make this choice between constant and file or prior simulation in the model input under solve settings. The constant initial heads option is often very useful for simulating something like a pumping test or a short transient dewatering situation, where what you're really interested in is simulating the change induced by some stress, pumping at a well or at a dewatering system. And you're not so interested in what the background regional flow pattern is, and so on. You can think of this as superimposing a model of the changes induced by the stress on top of the model of the prior unstressed condition. Only you don't have to make a model of that prior unstressed condition. You can just simulate the changes that the stress induces. And this turns out is exactly fine in a linear or unconfined domain situation, because those two models can be superpositioned perfectly. And it's approximately fine in other situations with, say, nonlinear domains like unconfined. And when you do a standard pumping test analysis, say the Tice solution or Hantuch solution or Newman for unconfined, you're making that same assumption. You're just simulating the transient change that the pumping induces. This is fine for that application, and where it breaks down is if you want to simulate the long-term evolution into a steady state. In that case, you'd need to run a transient model from an initial condition from a file. This slide lists where Anaqsim is going to need initial heads. It's going to need it at every basis point, because that transient term in the equation for the first time step needs an initial head. It also needs it, or wants it, electively for some of the analysis menu inputs, transient line conditions, hydrograph points, and at pumping wells, so that you can make nice plots. If you're going to run a simulation where the initial heads are from a prior simulation, then here are the steps you need to follow. You first build your transient model, but don't solve it, and then you save the initial head locations from that transient model. That would be the basis point locations and transient line condition locations and so on. Then you close that transient model and move to step 2, where you open and solve your prior simulation model. Maybe it's a steady state, maybe it's a different transient model. Either way, you then write the heads at the initial head locations that were defined in step 1, and then you close that model. And you go back to your transient model in step 3, and you solve, and when it asks for your initial head file, you point to the file that you created in step 2. I'll talk a little bit about the kinds of outputs you can generate in a transient model. For every time step, you can generate the same kinds of plots that you generate in a steady state model, contours of heads, vectors, and so on. And those can be done for each time step. What I'm showing here is a transient dewatering system with a perimeter sump around a pit. And this is early in the simulation. One really nice output that you can generate is a set of transient head profiles along a line at every time step in the simulation. And in this one here, it's an example where in the initial model at time 0, before the transient model set in, we had a well pumping at this location, and it was pumping at a fairly high rate. In the first period of the transient model, that well was shut off, and you get these curves here, this lighter blue and even lighter blue on up through the greens and the yellows and into the reds up to time 50 here. And looks like the water table or head recovered to kind of get rid of the cone of depression, for the most part. Then in the second time period, which goes from time 50 to time 100, the well turns back on, and at a lower rate though. So you get these curves, this red one at the first time step, barely into that second time period, and other subsequent time periods where it kind of stabilizes in terms of drawdown, but starts spreading further and further to the sides. In Anaqsim, you can get nice outputs of transient discharges versus time for all of these kinds of features: head specified wells, line boundaries, rivers, multi-level wells where you're not sure of the breakdown of discharge between the domains spanned. That can be output. And discharge across line boundaries on the external boundaries of the model, as well as vertical leakages over polygons or domains that you specify. All of these outputs can be generated either as written tables to the run log, written tables to a file, I think it's a CSV, delimited file, or to a graph, and that's instant. Very handy. Along the same lines, you can generate tables or graphs of head versus time at these features here, hydrograph points that you predefine. And you can generate either head or drawdown hydrographs. And you can get the heads at discharge specified wells. And you can get a hydrograph or head versus time plot of anywhere that you select by right-clicking over the plot. Here's an example of head versus time at a discharge specified well that turns on for a 50-day time period, and then its discharge is reduced after 50 days so that you get a decline in head over time in that second period. And this particular simulation, we have these two 50-day periods, 7 steps per period with a multiplier of 2.0. And the values, you can kind of see the kinks in the curve here. Those are basically linear segments between the reported heads at the end of each time step. Here's an example of plots that have been generated for a head specified well in a transient simulation. The simulation has 3 time periods of duration 10, 10, and 20 days, and the periods are broken up with 6 steps in each of the first 2 periods and 8 in the third. And the time step multipliers are 2 and then 1.5, 1.5 in the 3 periods. So initially, at the start of the simulation, the head was 20 at this location, and then at this head specified well screen, and it wasn't pumping. But in the first time period, the head was set to 12, and that required discharge higher initially to achieve that in the beginning of this first time period. And each of these stair steps is a time period, and the discharge required to maintain that head at 12 tapers off through that 10-day time period. And you can see in that same time period that head goes from 20 abruptly to 12 at the end of the first time step. In the second period, this head specified well is shut off. So the discharge is 0, and the head recovers back towards 20, which was its initial steady state condition. Then in the third period, the head is set at 6, even lower than the initial period of 12. So the head drops to 6 for the duration of that 20-day period, and the same thing occurs. It requires a strong discharge rate initially, and that kind of tapers off with time as less and less discharge is needed to keep the head at 20. Transient path lines can be traced in Anaqsim, and for these, the time increases in the direction of flow along the path line, and the flow field changes from one step to the next through the duration of the simulation. And you can only trace these transient path lines for as long as the transient simulation lasts. And I put an asterisk there because there's an option, which I'll describe in a minute, where you freeze the transient flow field and then trace as though it were a steady state, indefinite time period. Okay, so each time step has its own flow field, own solution, and for the duration of a time step, the flow field that the path line is tracing through is that fixed flow field for that step. To illustrate transient path lines, I've got an example model here that has 15 time steps, and each step is 0.2 days long. I used a time step multiplier of 1 just so it's easy to track when each step is. And I've got 4 plots. The first here is at 0.2 days, and the flow field has not yet changed from the initial one, which was kind of uniform flow towards the east. And what happens in this model is that somewhere to the northeast, a well turns on at time 0 and begins to affect the flow field. So the contours that are drawn here are for time equals 0.2 days, and this arrowhead is at 0.2 days into the simulation. And you can see that the flow is going perpendicular to these contours. So this next frame, it's time equals 1.0 days, and the contours are for that point in time. And that point in time on the path line is that arrowhead right there. And you can see, again, that it's flowing perpendicular to the head contours. And similarly, at 2 days into the simulation, here's the arrowhead that applies, and these are the contours that apply, again, flowing perpendicular to it. And here's at the end of the simulation, at 3 days, again, flowing perpendicular to those 3-day contours. So it's kind of a mind bender to think about the flow field shifting as this path line is evolving. To help you visualize this even better, I've taken that same simulation and made it only 4 time steps, each 0.75 days long. This is a much coarser time discretization. And when you trace the path lines in that model, you can easily see that here's the duration of step 1, where the flow was going this direction. Here's the duration of step 2. There's the duration of step 3 and of step 4. Now, I should note that the area of these plots is very small, and the flow moved very short distances in this 3-day simulation. So that's why it looks like it's a completely uniform direction of flow during the first time step. That's because the model itself is uniform, and the flow field at this little tiny patch was nearly uniform. The freeze transient option that I alluded to in an earlier slide is explained here. Basically, you're allowed to trace path lines through a snapshot flow field at a particular time in a transient simulation as though this flow field existed indefinitely, like a steady state flow field, and you could trace path lines as long as you wanted to. And the second bullet item there, I'm saying it's not scientifically sound, and I don't generally recommend it. The only reason I built it in was at the request of a user, because in Massachusetts, they require defining a well zone of contribution using a frozen flow field after 180 days of zero recharge, as though that flow field would persist forever. And it's kind of faulty logic, but yeah, there you have it. Let's discuss a case study to demonstrate the utility of transient modeling in Anaqsim. This was of a pumping test in a thick stratified sand aquifer, and the model had 9 layers as shown here, 3 layers in this lower conductivity material, and then getting a little bit more conductive, and then an extremely conductive layer here, and then a little bit less conductive going towards the surface. And the pumping well was a municipal pumping well that cycled on every day for 12 hours at 850 gallons a minute, and it spanned these layers in the model, and in particular this very high conductive layer up near the top of its screen. And the observation wells that were available to calibrate the model to were shallower and partially penetrating, as well as we had head measurements in the pumping well itself, and they did a borehole flow meter survey while it was pumping so that we knew how the discharges were distributed along the length of that well screen. This was an Anaqsim model where we used constant initial heads. Basically set the heads 0 everywhere in all levels, so that was the starting condition, and we simulated the deviation in head from this 0 initial condition. And the outermost boundary in all 9 layers was a head specified outer boundary that set a 0 gradient and used the average head, which was set to 0 in each of the 9 layers. And the outer boundary was set at a radius big enough that there was no transient impact reaching that far out, and we checked that. The SVAS basis points are shown here with these little plus signs, and the whole area was basically using the well basis point spacings that I think we used the highest setting. I think it was 10. Yeah, 10 points per circle, and that gave very good accuracy in terms of the storage fluxes that were simulated and the extraction check. Here's an output plot of head versus radial distance from the pumping well in each of the 9 layers at the end of that 12-hour or 720-minute pumping session. And you can see that the strong drawdown occurred in levels 5, 6, and 7, which were spanning the well screen, and lesser drawdowns in layers both above and below it. And all of these drawdowns, of course, taper with distance, and the drawdown at the pumped well is around 40 feet, which was a match to what was observed. Here are graphs of transient head profiles in level 1, which is up at the water table, well above the pumped well screen, and down in level 5, which is that most permeable strata at the top of the well screen. And you can see the drawdowns versus time for this 12-hour simulation. Only a few inches of drawdown, these are in feet here, up at the water table, but about 40 feet of drawdown at the well screen. Here is the simulated drawdown in the pumping well itself, which was a large diameter pumping well, 18-inch or something like that. And this matched very nicely with what's observed in the pumping well during a typical cycle. Here's the simulated discharge distribution coming into the pumped well. The discharge was specified and constant, but how it was distributed among the 3 different layers spanned by the well screen did vary some with time. We got about half of our total discharge, or a little more than that, coming from that thin layer 5, which was highly conductive, and lesser amounts in layers 6 and 7. And the distribution shifted a little bit from early time towards the nearly steady distribution we get late in the test, because early in the test there's more water coming out of elastic storage near the well, later in the test, more of the water is coming from water table storage and then flowing laterally and vertically to the well screen. So hence this shift in distribution a little bit from the earliest time steps towards the ultimate nearly steady situation later. Here is the Anaqsim model calibration comparing the simulated and observed hydrographs at those 3 observation wells. And for each of the 3 observation wells, there are 3 different dates when drawdowns were observed. And those are these shorter curves here in multicolors. And then the longer curves are the Anaqsim simulated curves. I guess some of the observed curves are long as well. But anyway, the model did a really nice job of matching the early time curvature, which is a function of elastic storage, the late time slope, which is a function of specific yield, and the magnitude of drawdown, which is a function of conductivities. Now, this kind of graph can be made automatically in Anaqsim, where you import observed data and then overlay model simulated data and make the comparison. Here are references that were cited during the slides, and one is the groundwater science textbook for its equations about storage parameters, and another is this USGS water supply paper with a nice compilation of specific yields for different materials, and a link there.